Good afternoon. Today I'm going to be going over my proposal for a new method to help 3D printing and the general stuff. This originally started by going over 3D printed houses, and I'll show kind of how I believe this could be applied to kind of more typical residential, commercial 3D printers. And yeah, I'll just get into it right now. Alright, so I'm going to at least initially start from the structure of a house, because I believe it really demonstrates, kind of helps visualize what I'm talking about here. So, currently, when we build a house, that's a foundation, we've got a wall. Okay, it's a pretty simple concept right here. When we see a lot of 3D printed houses and how they do their layers, because of the nature of 3D printing, we kind of get these circular, if not kind of more squashed ovular lines. Something like that. And this creates a very, if you ever see those kind of 3D printing houses, tour guides, it just doesn't look nice. It doesn't produce a nice effect, and no marketing, nothing can change that socially. You're not going to change the culture to make that, pleasing to the human brain. The answer is in the engineering, not in how you market a house or a new way of building a house. So, how can we turn this into this? Fundamentally, the question we're asking is a very old one. We have a circle, we want to square it. There's a very old idea, you might see sometimes they bring it up in conspiracy theory stuff, talking about squaring a circle. It's kind of a very old ancient practice, kind of, it shows how people understood geometry. And it's a nice representation. So in this we're trying to square a circle, but kind of different from here. Here we're building a square out of the edges of a circle. In our case, we're trying to turn a circle into a square, but in a very specific manner. We have to keep our vertical the same, okay? Because every increment still has to be the same. If we change the increment, then our kind of layer height, whatever we define that as, or it would be like a couple inches in a house, or like 0.2 millimeters in in kind of a more commercial 3D printer. We need to have that be consistent. We don't want to change the layer height. That'll also complicate things later. What we really want is we want to kind of smooth off kind of the edges of a circle. So I'll try and demonstrate it here. Imagine we have that. Imagine this is the center point line of a bunch of circles. We want this. We want a consistent across, and at some point the area running below, so we're going to call this X. This is our line. So at some point, kind of the amount of space occupied by these sorts of valleys, these valleys right here, these valleys, these kind of hilltops, the amount of area that within those hilltops will be equal to the amount of area within these kind of geometric valleys. So there's some point away from the center point line where these hills equals these valleys. And if a hill equals a valley and we kind of smooth it off at that X point, we're going to get just a square, which is what we want. So that's interesting. But like going back before, our layer height can't change. So switch back to kind of that squaring circle idea, right? So we have a set height. Okay, what is our set height equal to? Our set height has to be the same height as the height of a circle in this case. So the height of a circle is just going to be the diameter, at least in this vertical dimension for us. So that is going to be obviously start doing the equations, 2r, the radius twice, And then I'm going to draw our circle. And then we're going to, by definition, because of the whole hills and valleys, the width of our square is going to be less, and it's also going to be less of a square. It's going to be more of a rectangle, because we're going to have a different length this way than we're going to have that way. So some point like that, like that. So you see we still have area occupied over here and area occupied here, and we have, area missing here, area missing here, area missing here, area missing here. So that's like these are the valleys, the two valleys, and we have one peak. And we want the valley, the distance between the center point and this, which is x, defined as x, that is going to be where the area of these two combined equals the area of this. So, summing all that up. So, base times height. That is the formula for a rectangle or a square. We know our height. Our height is set. Once again, our height is 2r. Our base, we do not know. So I'm going to fix that r. Our base, we do not know. That's the distance we're trying to find. So let's try and find our base. Our base in this context, I'm going to redefine, instead of b, I'm going to redefine it to the variable w for our purposes. Alright, let's redraw this bigger so you can see it properly. Okay, so this is our circle. We've got our w distance, which is kind of, once again, the width or the base of our rectangle. And we got the r value, which is the radius of the circle. I'm going to use radius because of the area calculations. And then I have named these sections just for reference. I'm calling the single peak is defined as C, and then each valley, there's two valleys. The valley 1 is named A, the valley 2 is named B. Just for reference, they're the same on both sides because that's just because it's symmetrical. Our final x value won't matter which side it's on. Alright, so once we've kind of conceptually mapped this out, it's very, very simple. Very, very simple to understand. Because we have two shapes. This is just simple geometry. We have two shapes. We know that, typically I like to think of it as mass is conserved, but in this case area is conserved. So we can set them equal to each other. So with area of a circle, everyone's familiar with this equation, pi r squared. Is that we're converting a circle into a square. Pi r squared must equal base times height. Okay, well, we don't really know what our width is. That's kind of the value we're trying to find. So let's just keep that as w. Let's see, do we know our height? Yes, we do. Yes, we do. We know our height will have to be, because of the consistent layer height, it will have to be r. But that's only half. We want the diameter. But I don't really want to redefine it as diameter for our equation purposes and later canceling out. So we're just going to call that 2r. So we have we don't know our base, and we have our height. So we've got some consistent equations here. We're trying to find our w. So let's algebraically solve for our w. So we know that. We're going to divide both sides by 2r. So we're going to have w equals pi r squared divided by 2r. Okay, so yeah, once again, we've got that. W equals pi r divided by 2. So we've got our width. And the end goal, like I said, we're trying to find what point do you need to, I like to imagine it like, a concrete smoother, kind of a flat blade. At how deep do I need to run this flat blade and smooth out this circle in order to kind of, fill in the gaps of the valleys? That's what we want to know. So we have our W, but that's not how far in I need to hold it. Or how far away from the center of the circle I need to hold it, sorry. That is just the width of kind of our final shape. So in order to get how far away we need to be, we need W divided by 2. In this context, I've defined, we've defined it as half of this way. You want it distance from the center. So we know that x is what we're going to call it, that distance, equals w divided by 2. And we have our equation already. We did that. We already found w. W equals pi r divided by 2. So, if x equals w divided by 2, basically it's just going to be pi r divided by 2 divided by 2. But we can just combine those factors, and we can find that x equals pi r divided by 4. So, we know that for any circle we're going to do this for. If we know the radius of the circle, we can get that. We can get the radius, multiply it by pi, divide it by 4, and that is how far away you'll need to hold a smoothing tool in order to fill in the net valleys and peaks of a circle. So we've got our equation. We know it. So how does this apply? How does this apply? So imagine we had some kind of automated tooling device. We have something that goes along, moves along with the nozzle. And based on where the G code is following, it can orient itself and smooth off a wall. Smooth off a wall. And then as the concrete, if it would be a commercial building, was setting, or as if it was as the PLA, if in the case of commercial would be cooling, it would be able to fill in those valleys and those gaps. And to what end would this remove? Once again, no layer lines. That's the big point of all of this, in simple terms. This means if we can get this working sustainably with just one more extra, motor added to a system, kind of one more layer to that G code, you can basically finalize 3D printing. I mean, I feel like that is finally the one kind of major aesthetic difference between injection molding and the quality it produces and 3D printing is these layer lines. So if you can remove these by having something that smooths out, based on this, then you can remove layer lines altogether. And it's not a very complicated process. Like, it's all geometric stuff, very similar to what a lot of other 3D printing innovations. I certainly think a company should investigate this. I don't know if it's going to be Ender, I don't know if it's going to be Elegoo, I don't know if it's going to be Bamboo. A company should investigate this further, for sure. Because you get that smoothness like you get off injection molding or proper resin, but with all the simplicities of FDM. The only factor that kind of complicates it for more typical stuff, like commercial 3D printing instead of concrete. The reason I like the housing aspect is, one, because it's there's a lot more obvious application. Like kind of the amount more you could sell a product if it was a flat slab of concrete versus looking 3D printed. The kind of the revenue lost from that is a lot more extreme with kind of a housing manufacturing. And another advantage of the housing manufacturing is that you have a consistent nozzle size. With commercial 3D printing, we have our nozzle sizes, but they kind of range. Most printers have 0.4 nowadays, but you do see cases where, say, sometimes sell 0.2 nozzle kits, and so obviously these are diameters. But that will severely affect our X value. So if we have one integrated solution, then our R value is just naturally going to change, and then it might depend on how easy it is to wipe it, and you might have to have a different solution. So that's kind of a complication of this kind of commercialization process. But concrete and kind of the housing manufacturing, has more to gain, and also basically with those systems, you're not going to be changing the layer height consistently. You're going to be making a house, moving on to the next house, moving on to the next house, and you're going to have a very, very consistent system. Whereas in commercial 3D printing, hobbyists are going to change a lot of factors that you cannot control, and so it just complicates things. But if you were to have, a printer with a consistent thing, and you had this kind of movable, shiftable tool head kind of orienting around the nozzle and smoothing it out at the proper lines, if it solved layer lines, I think that would be a massive improvement. You don't have to do any sanding, you don't have to worry about any kind of, there's so many ways of acetone smoothing that I've tried to do, or sanding, that just leads to so much, extra cost, just such a pain, chemical risks. This is such an easy solution that, one more factor of G-code would probably be worth, it would be worth for a customer to pay an extra $50, $100 if every single time they printed, you got a significant improvement with no layer lines compared to any of your competitors. So yes, a company should investigate this. I hope you enjoyed this general presentation. Sorry I was a bit slow. I know the math is easy. I just wanted to take my time explaining it because I want people to really conceptualize just how easy this process is and how I kind of arrived at an equation of x equals pi r divided by 4 and get that through their head. So once again, thank you very much for watching. Let me know if you think this is a good idea. Should companies implement this? Does my math suck? It's pretty simple, but maybe I messed something up. Whatever concerns would you have about, a tool head, and if you're kind of an engineering type, how would you implement this? How would you make this kind of tool head that could smooth out parts? And, what do you think? Do you want this on your commercial printer? Et cetera, et cetera. Let me know. I am genuinely interested. And, thank you for watching all the way through. Have a great day.